present Pablo Bucaria will talk about clique and neighborhood characterization of strongly chordal graphs.
Okay, thank you. This talk will be about characterizations of strongly chordal graphs that can be obtained from characterizations of chordal graphs, and show some additional reasons to justify that strongly chordal graphs are called that way. So to start, we review the basic concepts. As you know, a graph is chordal when every cycle of length x4 has a chord, which is a mesh that connects non-consecutive vertices of the cycle. We say that the chord of a cycle, even then, is strong when it connects vertices that are at all distance into the cycle. And strongly chordal graphs are defined as those chordal graphs such that every cycle, even then, has, and additionally, if it has length at least 6, that cycle must have a strong chord. So, for example, in this graph, if we consider the outer vertices to form a cycle, that red edge is a strong edge because the vertices that are connected by that edge are at distance 3. But if we consider this other graph, and again we consider the cycle of outer edges, all the chords that that cycle has are between vertices that are numbered with even numbers. So the distances between those vertices in the cycle is not odd. So this is an example of a graph that is not strongly chordal. This graph is a special type of graph that is called the sign. More generally, we can define an end sign as a graph that is obtained from a cycle. We make the vertices of that cycle a clique, and to every edge of the cycle we attach triangles. And it turns out that a graph is strongly chordal if and only if it is chordal and sum-free. There are many other ways to characterize a strongly chordal graph. One of them is in terms of hereditary classes. For example, there is this characterization that says that a graph is strongly chordal if and only if it is a hereditary dually chordal graph, meaning that the graph is dually chordal and every induced subgraph is also dually chordal. And finally, there is a characterization found by Faber in terms of simple vertices. A vertex B is said to be simple when there is an order for its vertices, W1, W2, up to Wn, such that there is a contention between the neighborhoods, the close neighborhoods in that order. The close neighborhood of B is contained in the close neighborhood of W1, which is contained in the close neighborhood of W2, and so on. So this graph here is a small example of a simple vertex B. Its neighbors are W1, W2, W3, and we can clearly see that the neighborhood of W1 is contained in the neighborhood of W2, and in turn the neighborhood of W2 is contained in the neighborhood W3. We say that an ordering B1, B2, up to Bn of all the vertices of G is simple when for every I between 1 and n, the induced subgraph by B1, Bi plus 1 up to Bn is simple. Bi is simple in that induced subgraph. So the characterization says that the graph is strongly chordal if and only if it has a simple elimination order. So, well, once I gave the definitions, I will set the goals for this presentation. The goals are basically 3. The first of them is to use discrete parameters that are numbers obtained depending on the structure of the cliques of the graph to obtain characterizations for chordal graphs. And then when we have those characterizations, we try to add more conditions to them to obtain characterizations of strongly chordal graphs. And when that is done, we try to obtain very similar characterizations that use close neighborhoods instead of cliques. So to start, the first concept that is defined is the concept of clique strength. When we take a set S in the set of vertices of a graph G, we define the clique strength of S as the number of maximal cliques G that contain S. Whenever I say clique in this presentation, I am referring to maximum cliques. The clique strength of the set S is usually in the presentation written in that way. We say also that subgraph H of G is a strength K. Subgraph is the strength, the clique strength of the vertices of that graph is larger than K or equal to K. It is interesting to know that chordal graphs can be defined in terms of this concept. When we have one edge or we have one triangle of the graph, they are sets with clique strength 1 because the edges and triangles are sets of pairwise adjacent vertices, so they will be contained in at least one clique. So the definition of a chordal graph becomes this one. She is a chordal graph if and only if every cycle of a strength 1 edges either has a strength 1 chord, this is the case of cycles of length 4 and more, or is a strength 1 triangle. This is the case of what we consider a cycle of length 3. And the point in expressing the definition of chordal graphs in this way is that we can make it become a characterization of strongly chordal graphs that was proved by Mankey in 1999. It says that G is a strongly chordal graph if and only if for every number K larger than or equal to 1, every cycle of clique strength K edges either has a clique strength K chord or is a clique strength K triangle. This is for cliques. For neighborhoods, we can do something very similar. We will define now the disk strength of a set S as the number of different close neighborhoods that contain the set S in G. Similarly, we say that a subgraph H is a disk strength K subgraph. Its set of vertices is a disk strength K set. This small example shows that clique strength and disk strength are different concepts. For example, if we consider this edge, it is contained in only two cliques, this one and this one. This is the picture for disk strength. This edge is contained in the neighborhoods of its endpoints and also in the neighborhood of this vertex and of this vertex and of this vertex. Those are 5 vertices and they all have different neighborhoods. So we say that the disk strength of that edge is 5. And once again, we can say that the graph is chordal if and only if every cycle of disk strength 1 edges either contains a disk strength 1 chord or a disk strength 1 triangle, or is a disk strength 1 triangle. Similarly to the case of cliques, this also can be used to obtain a characterization of strongly chordal graph that is almost identical. We only change cliques by neighborhoods. says that the graph G is strongly causal if and only if for every k larger than or equal to 1, it happens that every cycle of this strength k edges either has this strength k chord or is this strength k triangle. Well, the proof of this property is by induction. We try to find a simple vertex B, and we consider the case whether B is in C or B is not in C. In any case, we try to use the special properties of simple vertices to prove the property. In the case that it is not necessary, we can consider the strongly causal graph G minus B and apply the induction hypothesis to it. This is for the way that the graph is strongly causal, then the property is satisfied. For the converse, if the graph is not strongly causal, then it means that it has an induced cycle of length at least 4, or it has a sum of size 3 or more. In the case that it has a cycle without chords, it means that it is a disk strength 1. It is a cycle with disk strength 1 edges that has no disk strength 1 chord, and since its size is larger than 3, it will not be a disk strength 1 triangle. For the case that it is sun, we should consider the cycle of length n whose vertices form the central creep. And for that cycle, the disk strength of every edge is n plus 1. But if we consider the set as a whole, there is no disk strength n plus 1 chord, and it is not possible that it is a disk strength n plus 1 triangle. To clarify this argument, let's consider the 3 sun. So the cycle that I mentioned in the previous paragraph is this one, and every edge of that cycle is contained in 4 close neighborhoods. For example, 2, 3 is contained in the neighborhood of 2, of 3, of 1, and 5. And something similar can be said about the other edges of that cycle. But however, when we consider all the 3 vertices of that cycle, it is not contained in 4 close neighborhoods. That triangle is contained in the close neighborhood of the vertices that form it, but no other vertex of the graph contains the 3 vertices of the triangle. So the triangle is formed by disk strength 4 edges, but it is not a disk strength 3 triangle. Okay, to continue, now let's introduce some other numbers. Now we will define Ci of G as the number of subsets of cardinality E that are contained in at least one clique of the graph. With that definition, we also define the clique characteristic X of G as the alternating sum C sub 1 G minus C sub 2 of G plus C sub 3 of G, and so on. For example, if G is the 3 sum, then every vertex is contained in one clique, so C sub 1 of G is equal to 6. Every edge is also contained in a clique, so C sub 2 of G is 9 because there are 9 edges in the graph. C sub 3 of G is 4 because the graph has 4 cliques of size 3. C sub I of G is 0 for any I larger than 4 because there is no clique of size 4 or larger. we consider x of g, it is 6 minus 9 plus 4, and it equals 1. This characteristic can be used to characterize chordal graph. This is a characterization by Marquis that says that the graph is chordal if and only if every induced subgraph h satisfies that this number x of h is equal to the number of connected components of h. We can do again the same. Okay, the same with closed neighborhoods. We will define now v sub I of g, g as the number of sets of cardinality I that is contained in at least one closed neighborhood of the graph. Again, we define this time using the neighborhoods, the parameter that is characteristic x hat of g, again as an alternating sum. And let's consider again the example of the free sum. For the free sum, we have that every set is contained in a closed neighborhood, provided that the 3 vertices are not all in the set, because any other set that does not contain the 3 of them is always contained in a closed neighborhood. So, taking that into account, we have that d sub 1 of g is equal to 6, d sub 2 of g is equal to 15, d sub 3 of g is equal to 19, d sub 4 of g is equal to 12, d sub 5 of g is equal to 3, and d sub I of g is equal to 0 for any other value of I. So x hat of g is equal to 6, well, to that alternating sum that is equal to 1. And again, the characterization is that a graph is chordal if and only if for every induced subgraph h we have that x hat of h is equal to the number of connected components of h. We see that in this example the condition is satisfied because x hat of j of g is equal to 1, and the graph clearly has one connected component because it is connected. This is to show that the condition is really necessary, because when we have a cycle of 4 vertices, x hat of C4 is equal to 2, which is different from 1, and for any other larger cycle, this picture shows what are the sets that are contained in at least one neighborhood. We can have single vertices, so the first term of x hat of Cn is n, and with respect to sets with 2 vertices, they can be the vertices of one edge or 2 vertices that are adjacent to another. So the second term of the alternating sum is 2 times n, and the sets of 3 vertices that are contained in one closed neighborhood are like this, the closed neighborhood of each vertex of the cycle. So x hat of Cn is equal to 0, which is different from 1. And how can this be used to obtain characterizations of strongly chordal graphs? To obtain characterizations of strongly chordal graphs, we generalize the concept. Now, for every natural number k, we define C sub a k as the number of cardinality I subsets contained in at least k cliques of G. When k is equal to 1, it is the same concept as before. We also define the same alternating sums x, k, g. Define the graph gk as the graph formed by the vertices that have Clique strength k and the edges that have also Clique strength k. So in the example of the free sum, there are 3 vertices that are contained in 2 cliques for the case of k equal to 2, and there are 3 edges that are contained in two cliques. So in this case, x2 of j is equal to 0, and g2 is the triangle at the center. The characterization of the strongly chordal graphs that we can obtain this way says that the graph is strongly chordal if and only if for every k and every induced graph h, it must be satisfied that xk of h is equal to the number of connected components of the graph hk. In this case, it was not true because for one number we got 0, and the number of connected components of K3 is 1. Well, and similarly, we can do exactly the same with closed neighborhood, define the same concepts using closed neighborhoods instead of cliques, and we again have the same characterization that says that a graph is a strongly chordal graph if and only if for every k and every induced graph, the two numbers, the alternating sum and the other, that is the number of connected components, are equal. Well, I cannot explain the proof because of the time. And if you would like to read more about this, you can go to this paper that was recently published, which has all the results. That's all. Thank you.
Any questions, comments? Let's thank the speaker again.